Have you ever stopped to think about how our entire digital worlds, everything from sending an email to playing a video game, can all come from something as simple as an on-off switch? Well, today, we're going to peel back the layers and go on that exact journey, from that one tiny switch to the incredibly complex world it powers. Okay, let's get into it.
So this is the big question, right? It feels kind of impossible. How could a concept this basic possibly lead to things like artificial intelligence or global social networks or stunningly realistic graphics? Well, it can. And by the end of this, you're going to see exactly how all those pieces click into place.
To get our heads around this, we have to start at the very, very bottom. We're talking about the fundamental language that every single computer speaks. It's a world where absolutely everything is described using just two options.
And here it is. Meet the bit. It's short for binary digit, and it's the smallest possible piece of information a computer can understand. It can only be one of two things, a 0 or a 1. Seriously, just think of a light switch. It's either off, that's a 0, or it's on, that's a 1. That's it. That's the entire alphabet for a computer.
Okay, but this is where it starts to get really cool. See, one bit by itself isn't all that useful, but when you start stringing them together, millions or even billions of them, they can represent, well, literally anything. Every word on the screen, every sound in your favorite song. At the end of the day, it's all just a super long, carefully arranged pattern of ones and zeros. Let's use pictures as an example, because they're easy to visualize. We take an image, and we break it down into the smallest possible pieces. We call these pixels. You can think of each pixel as just one tiny dot of color on your screen. And how does the screen know what color to make that dot? You got it. A specific string of ones and zeros tells it the exact mix of red, green, and blue to light up. And this shows you exactly what I'm talking about. A photo on your phone looks all smooth and seamless, right? But if you zoom in, and I mean you zoom way in, you'll see it's not smooth at all. It's a giant grid, a mosaic of these tiny colored squares. Each one is a pixel, and each one is being controlled by its own little chunk of binary data. Now, as you can imagine, all these bits add up fast. A single high-quality photo can have millions of pixels, which means the files get huge. To handle this, computer scientists came up with something brilliant: compression. There are two main flavors. You've got lossless, which is kind of like vacuum packing your clothes. You can get all the air out to make it smaller, but when you unpack it, everything is still there. Perfect for things like text. Then there's lossy. This is more like trimming the fat. It cleverly throws away tiny bits of data your eyes or ears would never notice anyway, making things like music and video files way, way smaller.
All right, so we've figured out how to turn our world into data, into ones and zeros. But data just sitting there is pretty useless, isn't it? We need a machine that can actually read all that information and do something with it. And that brings us to our next layer.
Every computer system really has two sides to the same coin. First, you have the hardware. That's the physical stuff, right? The silicon chips, the wires, the parts you can actually touch. And then you have the software. These are the invisible instructions, the programs and code that tell all that physical hardware what it's supposed to do.
Now, right at the very heart of the hardware is this thing, the central processing unit, or CPU. If a computer is a body, then the CPU is its brain. It's the engine that does all the heavy lifting, all the calculations, and executes every single instruction, from adding 2 plus 2 to building a complex 3D world in a game.
So how does this brain actually get anything done? Well, it runs on a constant rhythmic pulse called the fetch, decode, execute cycle. You can literally think of it as the computer's heartbeat. It's a simple loop that it repeats billions of times every single second to run our programs. Let's break that heartbeat down. First, the CPU fetches the next instruction it needs from memory, like grabbing the next item on a to-do list. Next, it decodes that instruction to figure out what it's being asked to do. Add these numbers or move this piece of data. And finally, it executes the command, actually performing the task. Fetch, decode, execute. Over and over, billions of times a second. It's wild. Okay, so we've got this incredible piece of hardware, the CPU, just humming along, ready to work. But on its own, it's just a really smart rock. It doesn't know what to do. That brings us to our next layer up, the software. You could call it the ghost in the machine. This quote really nails it. The earliest computers were a total nightmare to use. You literally had to be there physically flipping switches to get them to do anything.
The real game changer was the idea of an operating system, basically a master program that manages all the complicated hardware for you so we can interact with it in a much friendlier way.
So what is all this software actually made of? Well, when you boil it all down, it's made of algorithms. Now, algorithm sounds like a fancy, complicated word, but it's not. It's just a recipe, a set of step-by-step instructions for how to solve a problem. Seriously, the recipe you follow to bake a cake is an algorithm. The directions your GPS gives you is an algorithm. It's the logic behind everything software does. So far, pretty much everything we've talked about has been happening inside one single computer. But the real magic of our modern world, the thing that changed everything, happens when we connect them. So let's zoom out to the biggest layer of all, the network that links billions of these machines all across the planet.
You know, most of the internet runs on this really simple but incredibly powerful idea called the client-server model. It's easy. Your computer, when it's running a web browser, is the client. When you want to look at a website, your client sends a request out over the internet to a huge, powerful computer called a server. That server's job is to find what you asked for and serve it back to you.
And it feels instant, doesn't it? But behind the scenes, there's this incredible little dance happening every single time. You type in a website. Your browser asks something called the DNS. Think of it as the internet's phone book to look up the site's unique number, its IP address. Then, your browser connects to that number, asks the server for the page, the server sends it back in little pieces, and your browser puts it all back together so you can see it. All of that happens in the blink of an eye.
Okay, so we've gone from a single bit all the way up to the global internet. How on earth do computer scientists and engineers manage all of this insane complexity without their brains just melting? Well, the answer is one of the single most important ideas in all of computer science. This is the secret sauce. It's called abstraction. And really, it's just the art of hiding complex details behind a simpler front. Think about it. When you tap an icon on your phone, you don't need to know about the millions of lines of code running, or the fetch-execute cycles happening, or the binary data fly around. You just see a simple button that does something. That's abstraction. Each layer we've talked about today hides the messy complexity of the layer just below it.
So let's just recap the whole journey, right? It all kicks off with that simple little bit, a 0 or a 1. Those bits build up to represent complex data, like our text and images. That data gets processed by the hardware, which is chugging along with its CPU heartbeat. All that hardware is controlled by software, built from those step-by-step recipes called algorithms, and finally, all of it gets shared and connected through a global network. See? Each layer builds perfectly on top of the last one.
It's pretty amazing when you step back and look at it. We have built a world of almost unimaginable complexity, and we did it starting with the simplest foundation you can possibly imagine, an on-off switch, which really makes you wonder, what's the next great layer of abstraction going to be? What mind-bendingly complex system are we building right now that future generations will just see as a simple, elegant button they take for granted? That's something to think about.